everyone, in this video we are going to discuss ionization energy. But before we get started, I want to remind you that this is the third video in part of a three-part series, and so hopefully you watch the effective nuclear charge video first, then atomic radius, and now we're here on the best one, probably the hardest one though, which we're going to call ionization energy. So before I even get started on this, I want to say for those of you that are in my class, there was a fluorine example that I think caused more harm than good. So I want you to just forget about it and just pretend that didn't happen. Okay, so just forget about it. We're going to start over right here. So let's start with an example, excuse me, a definition. So ionization energy basically is the energy required to remove an electron. And this always happens in the gaseous state. Okay, that's just something that's kind of important. It's a condition that should be known, but just keep that in the back of your mind. So the first thing we need to do is talk about the difference between a first and second ionization energy. So the first ionization energy is essentially when you have an element X in the gaseous state, and what happens is we're trying to remove an electron, so we make it a cation. So we take away an electron and we create a cation essentially. Okay, so this is your first ionization energy. So when we talk about the energy component, that's what's written right here, and it would be some number kilojoules per mole. So essentially what we're saying is it takes not X, let's just say Z kilojoules of energy per every mole of reaction in order to remove an electron. So that's essentially what that means. So let's look at what the second ionization energy would be. So now this is one of the biggest mistakes that students make right here, is that they for some reason want to change this value or they want to keep it to be X, but second ionization energy literally means we're removing the second electron. So you can only remove a second electron if something has already had a first electron removed. So this needs to be an X plus. Okay, that's really what I'm trying to say here. So now, again, we're removing an electron. Nothing's changed here. So now this just becomes 2 plus. Okay, so the first one here, we're removing one electron. We go from neutral to a cation. And then the second one here, we're going from the cation, still remaining a cation. Our charge just increases. So we go from +1 to +2. Again, your ionization energy would be whatever number over here. We'll just say G, whatever, G kilojoules of energy per mole of reaction. So this right here, that's what we care about. These numbers, that's what we're analyzing. So the thing that I want to point out here before I get any further into this is that I want to look at this cation right here. Based on what we already know from previous videos, so our effective nuclear charge and our atomic radius, we already know that our X plus is going to be smaller in size than our neutral atom. Okay, so our cation is always going to be smaller than our neutral species. And so what that actually means is that the electrons are going to be pulled closer to that center, closer to the nucleus. So this is going to be smaller than this one. And that's a very important piece because we need to remember that as soon as we remove one electron, all the extra valence electrons immediately go whoosh and they get pulled closer in. So it is so much more challenging to remove that second electron. Always. That's just how that works because those electrons have been pulled closer in and they have a smaller atomic radius. Actually, I should be saying ionic radius because we're looking at an ion now. Okay, so now let's look at an example to hopefully concrete or solidify this concept. And so let's look at sodium. And so if we were to draw out the atomic orbitals in orbital notation of sodium, what we would have is something that's very simple. So we have 1s, then we have 2s, then we have 2p, and 3s. And so following all the rules, so Aufbau, now here's Hans, and then we're always following Pauli because we have one spin up, one spin down. And then for sodium, we're just adding that single valence electron. So again, I want to remind you, even though we've gone over this 6,000 times now at this point, that everything here is considered our inner shell. So that's going to be close, it's going to be pulled in. These are the ones that are providing electron-electron repulsion with this outer valence electron right here. So that's your valence electron. Okay, so now, if we're trying to talk about this in the context of ionization energy, let's start off by just looking at the first ionization energy of sodium. So we have sodium, again, in the gaseous state, has to be in the gas, and we're going to remove an electron. So this becomes sodium plus gas, and that's an electron. And so just to give you a frame of reference, to do this, to remove one electron from sodium, it's actually not that challenging, and it takes about 500 kilojoules of energy per mole of reaction. So kind of challenging. You definitely need to put energy in it, but it's not the most impossible thing in the world. Now, that is removing this electron right there. So let's say we've done that. This electron's gone. Okay, now we're looking at sodium plus. So we're literally just looking at these inner shell electrons because this outside one is gone. So now our second ionization energy. We have to start with a cation. We've already removed one electron. Now we're just going to remove our second electron, so this becomes sodium 2 plus, again in the gaseous state, plus a single electron. This process of removing the second electron, so removing this electron right there, okay, from the inner shell, actually requires approximately 5,000 kilojoules of energy per mole. 5,000 kilojoules of energy per mole of reaction. That's insane. That is so much energy. That's going to be incredibly difficult to do. That's not going to be something you just like accidentally happen, like whoops, just blew up some sodium there. That is not going to happen, okay? It requires so much energy, and that's because we are now breaking into this inner shell. So you should be thinking that there's this giant sumo wrestler right here, and he's ready to battle anybody that tries to come in to take any of his precious electrons, okay? Weird analogy, but think of it that way. So all of this put together on the micro scale, we can kind of compound to get a beautiful diagram. Again, gorgeous periodic table, it's a square. And what we end up seeing is that as we go across a period, we see an increase in ionization energy. And again, remember, that's because we see an increase of our Z effective. So we see a larger center here, a positive center, meaning that these electrons, these valence electrons on the outside, as we go across a period, are being pulled closer and closer and closer. So they're more tightly bound to the center of the nucleus. So to remove an electron from something over here is going to be incredibly challenging. You need to bring out like supersonic strength, like everything you possibly have in your arsenal to remove an electron. On the opposite side, so down here, it's going to be very, very, very easy to remove an electron. So our trend actually goes like this, okay? And so over here, these elements want to lose an electron, okay, these atoms. Over here, these atoms or elements, want to gain an electron. They desperately want to gain an electron. So if you look at fluorine, which has 1s, 2s, 2p, 1, 2, 3, 4, 5. Think about what's happening here. In order for somebody to come in or something to come in and remove that electron, I mean, I can't even tell you how much energy that would require, because all fluorine wants to do is gain an electron. That's all it wants to do. It's fighting everything possible to gain that electron. It does not want to lose an electron. It wants to gain an electron. And so what we see if we are overall talking about ionization energy is that our overall trend goes like this. So in this corner over here, it requires an insane amount of energy. So high ionization energy. It takes so much energy to remove an electron from the system. Whereas down here, very, very low ionization energy. It's super, super easy to remove an electron from fat old francium. Oh God, struggle with that. I guess that means I must be done with my video. Hopefully this makes sense. I really hope, I just want this to make sense to you guys so badly. So please email me if it's still not clear. We're going to move on and start talking about new stuff on Friday, but please come to office hours. Please come to the review. We are here for you to help. Have a wonderful week, guys. Take care of yourself and make sure you're drinking lots of water.